In this section, we're going to talk about yet another method for solving systems of equations. So far we know about the graphical method, but we didn't do graphical method in this course, but it's out there. We also talked about substitution, elimination. We saw an example of both of those, correct? Now what we need to do is we're going to look at yet another method of solving the systems. This time, matrix method. Now, first defining a matrix. What is a matrix? A matrix is simply a rectangular array of numbers. An array here is a listing of numbers. That's all an array is. Okay, so we're just going to have a listing of numbers that are arranged in a rectangular manner. So here's how the matrix would look like. So we have the brackets here. I'm going to go 2, 0, 7, negative 1, 4, 8, 11. They're just made up numbers, whatever they are. And this is what we mean by the rectangle. So if you think about this as a rectangle, I have 2, 0, 7, negative 1, 4, 11. Although they don't do it that way, but that's the impression of rectangle that we're talking about. Now, every matrix is made up of rows and columns. Okay, so the rows, of course, go in that direction. Columns are in the vertical direction. These are the columns, right? The rows are labeled from top to bottom. That's row 1, that's row 2. Columns from left to right. Column 1, 2, and 3. Now, if you look at the number of rows by columns, this is 2 rows by 3 columns. So we call that the size or the order of the matrix. Okay, so this is a 2 by 3 matrix. You don't need to don't write this. Okay, we know that's 6, but they don't do that. If you did, that just gives you the number of elements in the matrix. Each of the entries, each of the numbers is called an element of the matrix. Now, a 2 by 3. A 3 by 2 is going to look different, right? So for example, I'm just going to make this up, 1/2, negative 1, 4, 6, negative 2, 7. And this is a 3 by 2 matrix, so it has 3 rows, 2 columns. Okay, now the extent we want to work it in this section, we're not going to go too deep into the matrix method here, or operation with matrices. We just want to illustrate the idea of solving a system by matrix. Okay, so let's take a look at and see how we can actually write a system in a matrix form. Okay, so for example, here in our examples, again, sorry about that. In this example, we're going to look at exercise number 8. This is on page 551 of the textbook. Okay, in this example, the system is x plus 3y equals 16, and then 6x plus y equals 11. Okay, now in here what I need to do is first I need to write the system in matrix form. So in the matrix form, because I have 2 equations, I'm going to have 2 rows. The coefficient on the variables, the coefficient on x is 1, right? If it's not written, it's 1, so that's going to be 1. And then the coefficient on y is 3, the number by itself 16. In the second row, the numbers are 6, 1, and 11, correct? So those are the coefficients again. Now, notice we have a system, and the system was translated into a matrix that is 2 by 3. Okay. Now, we should be able to, by the way, go back and forth between the matrix and the systems. So before we actually solve this, let me just make up, for example, the system here. Suppose this is 204197. Remember, the numbers in the first column are the coefficients on x, second column are coefficients on y. So, and if I put a dot here, then the numbers to the right of that vertical dotted line are the constants, the other side of the equal sign. So the first equation is going to read 2x, 0y, let me just write it just so you see how that's written, equals 4. The second row is going to be 1x plus 9y equals 7. And of course, this we're going to write it as 2x equals 4 and x plus 9y equals 7. So let's write the system that's consistent with the matrix here. So for this one, again, remember the coefficient on the first column are attached to x. So the first equation is going to be 1x. And 0 means 0y, so you can leave that out, equal 3. The second equation reads x plus 4y equals 5. So actually, this is what the system looks like. Okay. Now, when we try to solve the matrix, when we try to solve the system, I should say, using the matrix method, what we would like to do is this. We'd like to transform this matrix into a matrix that's going to look like so. This first number is going to be A, B, C, and then we want a 0 here. 0, and then call that D and E. And because a matrix that looks like this, for example, suppose I have 5, 2, 7, and 0, 2, 8. Okay, a matrix, what's important is to have the 0 in that spot. Okay. The second equation in this matrix is going to read 2y equals 8, correct? Because 0 means 0x. And from this, we can easily solve for y. Y is 4. So this is, again, this is the goal of our matrix method for 2 equations, 2 unknowns. Okay. Now, in order to accomplish that, in order to achieve this 0 in that key spot, right now in that position, right now, see there is a 6. Okay. Now, in order to do this, we're going to do a set of what's called elementary row operations. Okay, and I have those listed below. And here they are. The book calls these row equivalent operations. But again, these are also known as elementary row operations. These operations are only valid on the rows. In other words, you cannot do these operations on the column of a matrix. Okay, just on the rows. So there are three elementary operations we are allowed to do with any system of equations or a matrix. You can interchange any 2 rows. Doing so is like write an equation that's in the 3rd position, in the 1st position, writing the first equation that's in the 1st position, like in the 2nd or 3rd. So switching rows is like switching equations, in other words. That doesn't make a difference in terms of the solution to the system. Okay. And then we have the second one. The second one allows us to multiply any row by a non-zero constant. That's basically the multiplication rule of equation. You can multiply any row by a non-zero constant. And the third row allows us to actually throw away and replace rows. We can replace a row if we don't like the way it looks by adding the row that we don't like and a multiple of another row. Okay, so that's what we're pretty much going to do in order to achieve a 0 here. Rule C. So let me go back up here, and actually we're going to do the elementary row operation here for this number -6 that's in here. Okay, we want to turn that into a 0. So notice if I switch rows here, that's not going to help me get the 0 there. Okay. And also, I know I said -6, but that's actually a 6. If I draw this correctly, that's going to make it look better. There you go. So that entry is a 6, not -6. Okay, so I want to turn this 6 into a 0. If I multiply a second row by 0, I'm not allowed to do that. And remember rule 2, you can multiply it by a non-zero constant. So I cannot multiply by 0. If I switch rows, right, if I interchange 2 rows or exchange them, that's not going to help me either. So part C, pretty much this is all I have to do in order to get a 0 in that key spot. Now, in that position right now, there sits a 6. We need opposite of that, right? Opposite of 6 would be -6. Now we can use the first row in order to do that. So I'm going to multiply -6 times the first row. That makes it -6, -18, and 6 times 16 is -96. And then add it to the existing second row, 6, 1, 11. And when we do that, we're going to get 0, -17, and -85. Okay, so that's going to be our new second row. Notice in doing so, although I multiply -6 times the first row itself is not going to change. It's called a helping row. It's just going to help us get to the second row. So it's not going to change itself. It just temporarily, think of it that way, it just temporarily and briefly changes to these numbers, and then these numbers, and then combines with that, helps accomplish the thing we wanted to accomplish, and then it goes back to being itself. Okay, now the new second row is going to be 0, -17, -85. Okay, now if you like, we don't have to, but because 17 and 85 are both divisible by 17, right? 5 times 17 is 85, so I can multiply second row, or let's say I'm going to divide, I'm going to do -117 times the second row. So that's 1/316. 1/17, that is -117, right? It's -117 times 0 is 0. -117 times -17 is 1. -117 times -85, that's 5. And there you go. If you look at the second row, it looks like this one. And indeed, right up here also, it did look like that final form that we were looking for. So from the second row now, from the second row, I can actually write the equation that goes with it. And now the equation is y equal 5. There, it's solved. To solve for x, we can back substitute in here or in here, either one. Okay, I'm going to go to the first one and do it for the first one. Okay, so back substitute in the first equation, I get x plus 3 times y equals 16. That's 3 x plus 15. Let me do x first. I was going to do 2 in one step, but I better not. So I'm going to subtract 15 from both sides, and that makes it 1. And x is 1, and we have the solution. The solution to system is 1, 5. And here you have it. So this is how the matrix method works for 2 equations and 2 unknowns. Now, let's take a look at the matrix method to solve 3 equations, 3 unknowns. Okay. I'm going to try exercise number 14 in this section. Okay, this exercise number 14 in this section. Now, in this exercise number 14, let me write the system to save time, and then I'll display it for you all at once. Okay, so I went ahead and put down the system for you. Now, we want to solve this system by matrix method. Now, in the case of a 3 by 3, by the way, this is what we would like to have in the end. A, B, C, D, 0 here, E, F, G, 0, 0, H, I, and there you go. That's what we would like to have. The key is to have this lower triangular formation of zeros. Okay, and that's what we're gonna do. So let's first write the system. The system is 4, negative 1, negative 3, 19, right? Only the coefficients or the numbers on the variables. No variables in this step. Negative 1, 11. And then I have 2, 1, 2, negative 7. And here's our system. Okay. Now, let's see. I see that the 4 and the 8, these are multiples of 2, right? So in other words, if I do 2 times 2, I get 4. 2 times 4, I get 8. So I can easily turn these into 0, couldn't I? And then I can accomplish the zeros that are in this column on my final matrix right down here. Okay, so I'm going to do that. In fact, I'm going to, we can actually write instructions for what I'm about to do here. Okay. So just to play around with this elementary row operation, I'm going to interchange row 1 and row 3. So here's how symbolically we write this. R1 exchanges with R3. The double-headed arrow means exchange. So row 1 is now 2, 1, 2, negative 7. And row 2 is 8, 1, negative 1, 11. And exchange with row 1, so new row 3 is going to be 4, negative 1, negative 3, and 19. Okay. Now, I need to get 0 below the 2, right? Right, I'm down here now. Okay, so I need to get this 8 to be 0. I'm going to multiply the first row by negative 4. That will make it negative 8. Add it to the second row and replace it. And that's what rule C up here tells me I can do. See, I can replace a row. In my case, I can replace the second row. Instead of a row, think of it as second row. So I'm going to replace second row with the sum of that row means second row, and a multiple of another row here would be first row. And this is how I'm going to write that. I'm going to do negative 4 times row 1 added to row 2. Okay, and that's what's going to happen. We're going to replace row 2 with that. Okay, now negative 4 times row 1. Negative 4 times row 1, that's negative 4. There you go. Negative 4 times 2, negative 8. Negative 4, negative 8, and 28. Added to row 2 elements are 8, 1, negative 1, and 11. And then add them. We get 0, negative 3, negative 9, and this makes 39. So that's going to be the new second row. Okay. So I'm going to write the first row. Remember, the first row is a helping row. It's not going to change itself. It's just going to help me get to the other rows. And the new second row is 0, negative 3, negative 9, and 39. Okay. Now, let's also, at the same time, let's do, this time I'm going to erase negative 4. Now, focus on the third row. There is a 4 here. We need to get that as 0. So I'm going to multiply this row by this time, what? Negative 2, correct? Negative 2 times that row. Notice I'm using row 1 again. That's why row 1 is helping us accomplish something here. So I'm going to multiply negative 2 times 2. That's negative 4. Negative 2, negative 4, and 14. The current third row is 4, negative 1, negative 3, 19. And then we're going to add them together. That makes it 0, negative 3, negative 7, and 33. Okay, so we're going to write that as our new third row. So what did I do again? I do negative 2 R1, we added to R3 to replace R3. The numbers are 0, negative 3, negative 7, and 33. So there we got the 2 zeros in that key spot. That's where we wanted it, and we definitely got it. So that's good. Now what do I need to do? I need to get a 0 right in here. This needs to become a 0. I'm over here now. See, we already accomplished the 2 zeros there. Now we need to get 0 in that key spot. Okay. In order to get a 0, I need the help from the row above. Okay, the second row this time. And notice, all it takes for this -3, actually this one, sorry, it takes for this one, it takes this to be a 3, I combine them and they add to 0, right? So what I'm going to do in this latest matrix, I'm going to do -1 times row 2, and then we're going to add it to row 3. Okay, row 1, 2, 1, 2, -7. That's unchanged. That's not altered. The second row itself isn't going to change, right? Because it's helping me now to get to the third row. Okay, now let's multiply -1 times row 2. Okay, -1 times existing row 2. That's going to be 0. -1 by -3 is 3. -1 by -9 is 9. And -1 times 39, -39. So I just multiplied -1, this -1, times all 4 of these numbers. Okay. And then let's write the existing third row. The existing third row is this row. I'm rewriting that one. In a moment, that's about to be replaced. And here's 33. Then we're going to add these. We get 0. There is the other 0 we wanted. Don't use row 1 at this stage. Okay, if you use row 1, you're going to lose this first 0 here. So use the second row in order to get this 0 in that spot. That's -6. 0, 0, 2, -6. And there you go. We accomplished what we wanted to. We got that lower triangular formation of zeros. At this point, we're going to translate the third row into an equation, which reads, remember, these are the numbers on X. The numbers in this column are the coefficients on Y. And the numbers in next to those are the coefficients on Z. Okay, so the third row reads, just to be complete, 0x, 0y, which we don't usually write, plus 2z equals -6. So there. And from this we get 2z equal -6. And divide by 2, so the solution to z is -3. A lot of work, huh? But if you don't have to explain it and do it, this doesn't take as long. And actually, this turns out to be a more efficient method of solving systems for larger systems, much better than elimination or substitution. Some kind of spirit of elimination in here because the way this is working out. Okay, now how do I solve for y, x and y? Well, at this point, because I know the value of z, I can actually plug this into the second equation, right? Which doesn't have x, it only has y and z, right? So that's what I'm gonna do. I'm gonna go to the second row. Let's write an equivalent expression to that second row that I just had pointed to. So for the second row now, I'm going to leave the 0 at this time, okay? So it's -3y, -9z equals 39. Okay, I just looked at, I don't know why this keeps popping up. I just looked at this one, this row. Okay, plug in a -3 for z. So from this we get -3y, -9 z equals 39. That's -3y. plus 27 equals 39. And subtract 27 from both sides, we get negative 3y equal 12, and divide by negative 3, so y would be negative 4. And there you go. And we need to solve for x, right? Well, first row here, this row is what I'm going to use. And we're up in the first row. Now the equation that goes with that is 2x plus y plus 2z equal negative 7. Plug in y and z in there, we get 2x plus y is negative 4 plus 2z, z is negative 3 equals negative 7. And solve for x, so we get 2x, negative 4, negative 6 equal negative 7. Combine like terms, that is combine the negative 4 and the negative 6 right there. Right here, negative 4, negative 6 combines and makes negative 10, so I'm going to add 10 to both sides. That makes 3 here, right? And next step, we're going to divide both sides by 2. So x is going to become 3/2. And we have the full solution now, x, y, and z. You see that? X, y, and z. All three are solved. And now we can just write it in as an ordered triple. And it's going to be the solution. 3/2, comma, negative 4, and negative 3. Right? That's what that was. And this is what the solution is. Okay. And there you have it. So that's to the extent that we want to do with this method, the matrix method. Now going forward, by the way, folks, I know this is like a lot of manipulation to get an answer, but this is just a passing section. In the future, once we move away from chapter 8, we're not going to be doing this. But nonetheless, it's worth mentioning it. And as I mentioned also that this is an efficient method, but it just you don't see the full matrix approach to this. But anyway, it is more efficient than the other two methods. So with that, we are done with this video, and we are done with section 8.6.